Okay, this is the second part of 904 where we introduced moment of inertia and torque. And in this video, we're going to look at some sample problems for torque. And I picked ones that were more conceptual, again, to align with AP. You might have some mathematical, we have some mathematics worked into these. So let's go ahead and jump in. All right, so I have a uniform ladder of mass m and length L rests against a smooth wall at an angle theta as shown in the figure. What is the torque due to the weight of the ladder about its base? Okay, so first of all, we need a pivot point. So let's say if this thing's going to fall, it's going to slide this way. So we're going to make this the pivot point. So when we have an object, we know that everything operates as if it's when we're talking about the weight, the force of weight acting on it, that we are looking at the center of mass. So if I had to draw a free body diagram, I would have some tension vectors here, but those are going to be not necessarily perpendicular. So the only one we really have to worry about here is gravity. And on an object like this, gravity is going to operate at the center of mass. Now they give us some rungs. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 3, 4. So I'm going to have a weight vector here, force of weight. But what we said in the last video is that only the components of force that are perpendicular to the object are going to apply. So I should have told you guys to pause it and take a look at this before we started. So I'm going to draw my components. So what we see is that we have an angle theta here. What we're going to see is that this component of weight, and by the way, how do we find weight? Yeah, mass times gravity. So the only component that's going to have an effect is this. And let's go back to our definition where we said torque is force times lever arm. So the force that I'm going to have is this one. Now I am, so how am I going to find this? This is an adjacent leg. So this is going to be a cosine theta function. And when we look for, when we simplify this, we're going to have mass times gravity cosine of theta for this force. Well, what about our lever arm? Well, we can see that the lever arm is 1/2 of the length. So we're going to say the lever arm is equal to 1/2 L. So that gives us mass times gravity times cosine theta times 1/2 L. When I simplify this, I can put that 2 on the bottom and I end up with mgl cosine theta over 2, which is letter D. So let's just sum this up. So what we had to do is we had to come back to our definition of torque, which is force times lever arm. We had to see that our lever arm is going to be operate at half of the distance. Now, you probably wouldn't have known that before this practice problem, and that's why I put this one in. So anytime we have an object that is in this kind of position, we're going to be looking at the force of weight or the force of gravity operating at the center of mass. And then we had to also know that we're only going to do the perpendicular portion and that the lever arm was going to be halfway through. Okay, let's move on to the number 2. For this one, pause the video and see what you can do with it. We'll read through it first. I have the figure above represents a stick of uniform density that is attached to a pivot at the right end and has equally spaced marks along its length. Any one or a combination of the 4 forces can be exerted on the stick as indicated. 2 of the 4 forces are exerted on the stick. Which of the following predictions about the change in angular velocity of the stick is correct about the change in angular velocity of the stick per unit of time? I think a good place to start on this would be to find the torque that would be exerted for each of these. So keep in mind, if this torque is exerted, it's going to push the bar this way. And if this torque is exerted, it's going to push the bar this way. But if this torque is exerted, I'm going to switch colors here because we have different things going on. The bars are going to move this way. So back in the intro chapter, we learned that if we're going to move counterclockwise, that's going to be positive. And if I'm going to move clockwise, sorry, I said that backwards, didn't I? Shoot, I drew these backwards. I'm not going to recopy. I'm just going to write these out. So let's go this direction. But that drawing error I just made is kind of probably one of the classic mistakes for these problems. So these are going to be negative because they're going clockwise. Counterclockwise is positive. Likewise, I know that when I multiply and when I find the torque, it's force times the lever arm. So here I have 200 newtons is my force, and I have a 0.5 meter lever arm. So this is going to be 100 Newton meters. Here I have 100 newtons, and I have each of these increments is 5. So this is going to be a lever arm of 1. So this is also going to be positive 100 Newton meters. Here I have a force of 50 and a lever arm of 1.5. So this is going to be negative 75. And here I have a lever arm of 2 and a force of 25. So this is going to be negative 50. Okay, so let's look at what we're looking at. When F1 and F2 are exerted on the stick will have the greatest change in angular velocity per unit of time. When F1 and F3 are exerted on the stick will not change its angular velocity per unit of time. When F2 and F3 are exerted on the stick's change in angular velocity per unit of time will be clockwise. Let's start with this one. So if we put F2 and F3 to work, they're saying that we're going to result in this motion. Well, we can see that's not going to be true because I have 100 Newton meters pushing this way, but only 75 pushing this way. So my net between here is going to be positive 25 Newton meters, and that's going to give us a counterclockwise. So this one's not true. When F1 and F3 are exerted on the stick will, that should say not, typo, change its angular velocity per unit of time. F1 is positive 100, F3 is negative 75. So again, I'm going to have a positive 25 torque involved. That's not going to be true. So we want to know, are F1 and F2 the greatest and are F1 and F3 the smallest? So F3 and F4 would give us a clockwise torque of 125 negative. But if we added up these two, that would be greater. So this one's not true. So it's looking like we're coming down to A. If we put F1 and F2 together, that's going to give us a plus 200 torque in the counterclockwise direction. And this one is going to be true. That's the biggest torque that we could exert on this bar. But you can see how these problems are multi-layered. So I had to first understand the definition that torque is force times lever arm. And then I had to use that to calculate the torques here. And then I had to analyze the combinations. And so that's pretty typical of an AP problem. All right, last practice problem for this video. Again, if you want to work on this on your own, you can pause the video. Let's go through it though. An axle passes through a pulley. Each end of the axle has a string that is tied to a support. A third string is looped many times around the edge of the pulley, and the free end attached to a block of mass, it should be M sub B, which is held at rest. When the block is released, the block falls downward. Consider clockwise to be the positive direction of rotation. Frictional effects from the axle are negligible, and the string wrapped around the disc never fully unwinds. The rotational inertia of the pulley is 1/2 mr squared about its center of mass. And they want to know, what are the total number of forces? What are the total number of torques? So when they say total number of forces, they're talking about translational or straight lines. So this is going to be translational. And this is going to be, torques are going to be rotational. Now, we have a side view. One of the things that can really, that students often miss is you have to read this direction. So the end of an axle has a string that is tied to a support. A third string is looped trying to remember how to, which is held at rest. So what you had to take out of this problem, and I think this one's kind of a stretch. If I look at this from the front, so here's my front view. This is my axle. And you notice here it says a third string. So this implies that there's 2 strings to start off with. Well, what you had to pull out of this problem, again, and this is where 95% of students miss, is that there's a string here and there's a string here and the ceiling is up here. And then you have the block down here that's attached, according with a third string. So if you didn't catch that this third string, this is a third string and that there's 2 other strings, this one was a little bit of a problem. So what we need now is our free body diagram. So what we're going to do is we are going to consider the axle. I've got gravity acting on the axle. And they're asking, do they specify rest blocks released? So the implication is that we're looking at the forces on the axle. So I have 2 tension values. I have a force of tension here. I have a force of tension here. I have gravity here. And then I have this force of the block mass MB. So these are all going to be straight line forces. And here's another toe tripper. Now, you might have said, well, wait, what about if we're looking at this as a system? What about the force that's at work on this block? Well, notice they don't give us 5 as an option. We've got, I'm a little off screen there. We've got 4, 4, 2, 2. So that means that we can't be looking at this force. If you wanted to add like another force here, that wouldn't work because we can't have 5. So we've got 4. And then which one of these is causing rotation? This one's not, and this one's not. It's holding the axle steady. This one's not. These 3 are equal and opposite. But this force of the block pulling the pulley down is going to turn this axle, and that's going to give us torque. So our answer here is going to be B, or straight line forces and 1 torque. So what this problem really shows you is that for AP, the devil really is in the details, because we had to realize that just because of this little word third here, that this was our assembly. We also had to know that, we couldn't include this, that we're only looking at this system because of the answers, narrowing it down for us, but that's also a test strategy. Use the answers to help you reverse engineer diagrams or things that you need to do. You'll notice too, as we're doing more and more AP practice problems versus just kind of straight up calculations. And that's kind of trying to keep us consistent with what we're going to be doing on the test. Okay, that is it for the practice problems for torque. I will see you in the next video when we look at torques on an entire system.